Metabolic engineering is the technology that underpins biosustainability. So this means that we can produce many of the materials, foods, feed ingredients, pharmaceuticals that we use in our daily life in a sustainable fashion. We are recruiting microbial cells to produce different chemicals of interest. And so we are engineering their metabolism. Often what we do is we use genetic engineering in order to change the genetic landscape, and so its metabolism is changed. When the field started, it was very hard often to do these genetic modifications, but this has really changed in recent years. So now I would say the biggest challenge we are facing is actually the design phase. How do we design which modifications we should introduce? And this is where the DD-DeCaF project comes into play.
So we were trying to make a project to speed up the design of cell factories and microbial communities for biotechnology applications, focusing on industrial biotechnology. We wanted to bring together some of the best people in Europe in academia and industry working on cell factory design and related technologies.
There was a metabolic engineer here at DT Biosustain that came up with a pretty interesting strain design idea that would actually force the production of a certain product to the growth of the organism. And then he went to a modeler and asked, like, what would a model say about that? Does the model confirm like my idea? And the model basically confirmed it, and then it was implemented and it was a huge success. But I always thought, like, was it really necessary to go to a specialist and ask this question? Could like this person have answered the question on his own? So when the EU announced a call that was about leveraging omics data in the context of biotechnology, we saw like an opportunity to apply for a project that would build a proper software platform. We wanted to achieve with this platform that this person can go and basically, click together. I want to knock out this gene. I want to have this particular component in the medium and, create a certain auxotrophy, and then like figure out, does the model confirm like my idea? And I think very early on we did a user test with this person just to verify, did we achieve this goal? And we achieved this goal. So the idea of the project was to bring together like experts in the field of metabolic modeling and getting access to the most cutting-edge developments in those fields, and then integrating all of this into the software platform and making it accessible to bench biologists that don't have the capabilities of programming or mathematical modeling, but they should reap the benefits of using those models. So basically all the things that biologists can do in the lab, like knocking out genes or changing the environment by using a different medium, you can do on the platform by clicking things together. For example, if you hover over this metabolic pathway map and you zoom in, then you also see more context. So if you zoomed in enough, then you see all the genes that encode like the enzymes that are catalyzing all those biochemical reactions, and also like their relations. So if you click then on the gene, you get the option to delete it. And if you delete it, then automatically the model will be re-simulated and like give you a new prediction of how this mutant might react. And that's pretty useful for predicting what experiments to do in the lab in order to achieve a certain production goal.
I'm a strain engineer, so we use genome scale models a lot in our daily work. Before we have to collaborate with another expert in the modeling and coding, but now with this platform we can easily do those work all by ourselves.
Where the DD-DeCaF project has really assisted with bringing forward metabolic engineering has been that it has assembled a team of world leaders in different areas, and so that has allowed us to combine different modeling components with bioinformatics, visualization tools into one common platform that can then easily be used by companies that are in the space and wants to exploit and particularly then speed up the design of new cell factories in the future.
Yeah, I'm a principal scientist in the DSM Biotechnology Center. I firmly believe that industrial biotechnology R&D will be more and more data-driven. So computational tools that are developed in the DD-DeCaF projects will be essential to drive the iterative design, build, test, learn cycles to speed up the R&D process. The platform collects a number of very powerful computational tools to analyze metabolic networks of microorganisms. And I have actually been testing the platform. And my experience is that the platform is very intuitive, easy to use, very interactive, and it provides very attractive visualizations. And for an industrial environment, it's very important that the platform can be run locally and compliant to corporate ICT regulations.
A big part of designing cell factories is actually identifying the genes that you're going to put into the cell factory for pathways that will make different chemical products. And for that purpose, we developed the largest microbial gene catalog that there has ever been developed. Over 2 billion genes were cataloged and functionally annotated, functionally categorized. And this is now available to everyone. And this really will accelerate the development of new cell factories.
When we produce certain chemical, and some steps of the pathway is we have to use genes that are not native to E. coli. And the platform actually could suggest candidate a list of genes and reactions from the database. And we can also it also suggests manipulation steps of E. coli genomes, and we can even visualize those steps and those changes, how it changed the whole metabolism for E. coli, for example.
With like so many cutting-edge developments on the biology side, like with CRISPR-Cas9 and so on, it's really easy to do a lot of manipulations simultaneously now, which was not the case like a couple of years ago. So I still remember as a modeler, models would return predictions of like knockout 5 genes and many more things, and biologists would be just like, but we can't do that, so, and then just ignore predictions. But now it's actually, we ended up in a situation where we can just not generate enough ideas to actually implement in the lab. And I think that's where like these tools can also be very handy in creating like a lot of diversity in terms of designs that could be implemented.
Genome scale models have developed a lot in these years, so I think it is not a proof of concept anymore. It should be used for molecular biologists or strain designers to, in their daily life and in their problem solving in their design as a routine tool to help them. And I think this platform serves as a bridge because you don't need a coding background. You can easily get access and get your information.
We early on realized that there is also an issue with like the quality of like some published metabolic models. So in order to avoid like, non-expert users uploading those models and then, producing results that don't make sense, we got together all the people from the consortium, but also like a lot of experts from outside the consortium to agree on a set of standards, quality standards for those models. And we encapsulated those standards into like a easy-to-use software package where literally you can go on a website, you can drag the file that you just got out of a supplementary file from a publication, you can drag it on the website, and like 20 seconds later it will spit out a report that tells you all the issues that this model might have. Like, for example, producing energy out of nothing or not being mass balanced. And I think that's very important in order to avoid users being disappointed in like wrong results, like later down the line.
The project also focused on understanding and designing microbial communities. And these communities could be something used for industrial production, as in starter cultures for yogurts or cheeses, or communities that live in our guts, where they play an important role in our health. We developed a comprehensive suite of tools and methods to study microbial communities, to model them, and to make predictions about how to design better communities.
Beyond the scientific successes that we had, and also getting this platform adopted in industry, It's very exciting for me to see that it's also people out of the team are forming a company.
Within the DD-DeCaF project, we have some of the researchers working at the forefront of community modeling. And we are now taking this cutting-edge science and bringing it into a spin-out. We have quite a bold vision. So we want to bring to consumers the possibility to optimize their personal diet. And when we're successful with this, we actually would like to take this to a clinical level. So it could become standard testing in hospitals and in the healthcare sector in general. And beyond that, there are many other application areas. I think we are just starting to scratch the surface of where do microbial communities play an important role. And we are finding more and more areas. So I think this approach of community modeling has huge potential.
In this project, we promise to develop new models, methods, algorithms, software tools for designing cell factories and microbial communities. I think we succeeded beyond our expectations. We really developed a broad range of methods that apply to different organisms and different types of communities, and also made them available through our software tools.
I think one of the greatest results that have come out of the DD-DeCaF project is that there has actually been a product in terms of a software platform that can really be used a little bit like a CAD system in the architect world and design, traditional engineering disciplines, where you can now begin to kind of lay out what design do you want to have of your metabolism in, for example, your baker's yeast, such that you efficiently can produce new products. And I think that will speed up significantly bringing new products to the market that are produced in a sustainable way.
The scientific and engineering consortium behind this project has been great to work with. It's very international, all over Europe with different kinds of competencies, but also very harmonious, very well functioning. Everyone is excited to work together. So many of the people in this consortium will also continue working together in other European Union funded projects or other scientific projects, and that's a great sign that the project has really been successful.